So this lesson is going to be a bit of an overview of the handouts that I've attached to today's lesson. The first attachment in terms of applications, just looking at a graph, I felt that was pretty straightforward, so I didn't really do a video for that one, but I am going to do a video for this one, just because it's slightly more complex. So we'll walk through the first example here. A penny is dropped into a tank of water at the water's surface. As it falls to the bottom, its pathway can be modeled by the relation here, where d is the depth of the water measured in meters, and t is time in seconds after the penny was dropped. So complete the table of values by substituting the values of t, whatever our time interval is, into the equation to find the depth in meters. So we can see that here. When time is 0, we plug that into where that t value would be from our initial equation, right? Negative 3.5 t squared plus 35. That's the relation. The time value is 0. When we plug that in, we get a value of 35. So at time 0, the depth is 35. So it starts here. And then when time is 1, we plug that into the equation, and then we get a depth measure as well. And then we kind of keep going, and we get our values, and we can eventually see how that graph would look along the Cartesian plane. So graph the data and draw the curve. Done. How deep is the tank of water? Well, the penny starts at the top of the tank, which is 35 meters, right? Because it's set up at top here. The water's surface, which we found to be 35 meters. Approximately how long will it take for the penny to reach the bottom of the tank? So again, if we just kind of look at the graph here, so how long does it take to get to the bottom? Well, it takes just over 3 seconds. And if we look at the graph, we can just say, okay, it's about 3.1 seconds. So that's one way of doing it, but there is a method to find the exact time. So in order to do that, we need to plug in and use this equation here. So at the bottom of the tank, the depth is 0, right? Because it's at the exact bottom. So we have our equation here, d equals negative 3.5 t squared plus 35. Well, if the depth is 0, our d value is 0. So now we have 0 equals negative 3.5 t squared plus 35. Now we can solve for the value of t, or the exact time. And we do that by solving for the variable, right? Subtract 35 from both sides, opposite operation of, we end up getting a value of 3.16 seconds, right? So that is exactly how long it's going to take the penny to drop. And we are pretty close with our estimation simply by looking at the graph. Let's do another one here. A textbook falls from the top shelf of a shaky bookcase. The path of the book can be modeled by the relation h equals negative 9t squared plus 90. Right? There's a relation where h represents the height of the book above the floor in centimeters, and t represents time in seconds. Right? So this is the height, and then t is time. Use the equation to find the height of the top shelf. Well, at the top of the shelf, there's been no time, right? That's where it starts. So we're trying to find that y-intercept, or when our time is 0. So we basically plug 0 in, and we can find that the top height of the shelf is 90 meters. Right? It's also indicated here because it's written in standard form for us. Use the equation to find out how long it takes the book to reach the floor. Okay, so how long does it take for it to get down to the ground? So on the floor, the height value is 0. So we know that h is 0, and then we can solve for the exact time, which is represented by the variable t. So when our height is 0, our time is exactly 3.16 seconds. Actually, the exact same as the above example. Use the equation to find the height of the book at 2.5 seconds. So what this is asking is, how high is the book when the time elapsed has been 2.5 seconds? So we're given a piece of information here. This is our time value. So we sub in our value for time into our equation like we've done here. And then we simply solve for the height, which is 33.75 meters. That should be centimeters, but 33.75. So what that means is that at 2.5 seconds, it is about 33.75 centimeters off of the ground. Our final example here, Michael owns a trampoline. He wants to see how high he can jump. The path of one jump can be modeled by this relation here, negative 4t squared plus 80t plus 12, where h represents Michael's height above the ground in centimeters, and t represents the time in seconds. So what is the height of the trampoline? Well, we're looking for that y-intercept. We know that the time is 0, nothing's happened yet. So when time is 0, we know that our c value in standard form is our y-intercept. So the height of the trampoline is 12 meters. How long does it take Michael to reach his maximum height? Well, it takes him 10 seconds, because we can see by the graph there. What is Michael's height after 5 seconds? Okay, so it gives us the time. So 5 seconds is right around here. So we visually see, we can kind of get an idea of where it's going to be, but we can figure out the exact height by plugging in our time value of 5 into our equation, which we've done here. So when we plug in the value of 5 for our t variable, we go ahead and solve, and we determine that the height after 5 seconds is 312 meters. And that basically makes sense, right? If we look here, we see 5, we kind of go up, yeah, it's just over 300. And based on this scale, 312 is about, makes sense. How long is Michael above 300 centimeters, right? So we look at this graph. So this is the 300 mark. It is above 300 for how long? So we're looking for between 5 seconds, and it looks like it comes down at 15. So it's approximately between 5 and 15. So that means he spends 10 seconds above 300 centimeters. I don't know why this is in meters, it should be centimeters. Okay, so takeaways from this, when you're given, I'll use this one as an example, when you're given the relation, we're stating what our h and t represent. Look at what it's asking you, and then you're simply just going to take the information that you're given, such as something like this, and then plug it into the equation and determine what it is that is being asked for you to look for, right? So it's very much take the information, plug it into the equation to determine what it is that you're being asked to find.